For 20 years, the science of red light therapy has had a tidy explanation for how it works. That explanation isn't wrong, but a physicist named Andrei Sommer has spent a decade showing that it's far from complete, and what he found may change the way we think about light, cells, and the biology of ageing. The dominant model in red light therapy goes like this. Red and near-infrared light is absorbed by a protein inside the mitochondria called cytochrome C oxidase, CCO. That absorption improves how mitochondria function, increases ATP production, the energy currency of the cell, and triggers a cascade of cellular benefits: better collagen synthesis, reduced inflammation, faster tissue repair. It's a clean mechanism, and it has solid research behind it. But there are things it doesn't explain. Wavelengths like 1064 nanometers used in certain medical lasers produce measurable biological benefits, even though CCO barely absorbs light at that range. Blue light, which CCO absorbs more strongly than red or near-infrared, often leads to reduced ATP production and increased reactive oxygen species, ROS. And different cell types with very different levels of CCO respond similarly to the same light. According to the dominant model, none of that should happen. Something else is going on. And the answer, according to Sommer, is in the water.
Hi, if we've not met yet, I'm Bev May-Sanderson, founder of MAYSAMA. Welcome to our LED Intelligence series, where we delve deep into the science of photobiomodulation, what's new in published peer-reviewed research, advanced LED technical engineering, and the biological relevance of how cells interact with light. We would love you to hit that subscribe button and join our community. And if you have any questions, please drop them in the comments below. I read every single one and I genuinely love these conversations. Now back to the video.
Andrei Sommer is a physicist and nanotechnologist at the University of Ulm. His central proposal is this. The primary target of red and near-infrared light is a form of water that exists in extraordinarily thin layers around the structures inside your cells. Most of us know water in three forms: liquid, solid ice, or steam. But inside the body, a fourth phase exists. First described in detail by Dr. Gerald Pollack at the University of Washington, it's called structured water, or exclusion zone water, EZ water. It forms wherever water meets a biological surface, around membranes, proteins, and the inner folds of mitochondria. Unlike ordinary water, it has a gel-like consistency, thicker, more viscous. Sommer describes it as closer to treacle than water. ATP is produced by an enzyme called ATP synthase, a molecular motor operating at the nanoscale, spinning inside the fluid of the mitochondrial membrane. Like any motor, the thicker the medium it's working in, the harder it has to work, and the less efficiently it runs. If the water surrounding ATP synthase is viscous, the motor is fighting resistance with every rotation, and less ATP is produced as a result. This is where light comes in. Sommer's team applied 670 nanometer laser light to an artificial membrane model and used atomic force microscopy to measure what happened to the surrounding water layers, a technique sensitive enough to detect changes in stiffness at the nanoscale. The result was immediate and measurable. The water softened, the viscosity dropped, and the treacle thinned. When the motor is no longer fighting thick water, it spins more freely, and ATP production rises. In this model, red light doesn't hit an on switch so much as it removes a brake, and the brake is the viscosity of the water around your mitochondria. This also explains something that anyone using red light therapy should understand. More light does not mean more benefit. At a certain point, it means less. As treatment continues, a natural byproduct of increased ATP production accumulates, reactive oxygen species, or ROS. In small amounts, these are biologically useful, acting as a cellular signal that triggers repair and regeneration. But as they build up between the interfacial water layers, they increase viscosity. The treacle returns, the motor slows, and ATP production plateaus and may decline, despite the fact that the light is still being applied. This is the biphasic dose response, described in biology by the Arndt-Schultz law. Small doses stimulate, larger doses inhibit. What Sommer's model provides is a biophysical mechanism for exactly why this happens. Short, well-timed exposures allow ROS to clear before the next session begins, and pulsed light protocols work on the same principle, building in the rest cycles the system needs to reset and benefit again. There is one further dimension worth considering. As we age, the viscosity of structured water inside our cells naturally increases. The gel thickens and the motor slows. Sommer proposes this as a biophysical driver of age-related cellular decline, which offers a new way to understand why aged or sun-damaged skin responds so well to red light therapy. The cells have been working in increasingly thick water, sluggish and energy-starved, and the light frees them. In this model, aging is partly a hydration problem at the cellular level, and light is one way to address it. Sommer's model doesn't replace the CCO hypothesis. Both mechanisms likely coexist and possibly interact. What it does is widen the picture, shifting the focus from individual protein targets to the medium those proteins operate in. Light interacts with molecules, yes, but it also interacts with the water between them. And in a body that is roughly 70% water, that is a very significant distinction. If you found this useful, please share it and drop your questions in the comments below. See you on the next one!